a few people are dribbling, but I think we'll get going at this stage. So welcome back to the second part of the Quantum Information and Computation session. It's my great pleasure to introduce my long-term colleague, Andrea Morello from the University of New South Wales. Andrea is an electrical engineer and quantum physicist and a professor of quantum nanosystems at the School of Electrical Engineering at UNSW. He's also program manager in the Australian Research Council Centre of Excellence for Quantum Computation and Communication Technology. His work is based on building a quantum computer based on single spins in silicon, as you'll hear. And in addition to his research, Andrea is very actively engaged in science outreach and education. So Andrea is going to talk to us about operation and scale-up of donor-based.
Thank you, Andrew, and thanks to the organizer for inviting me here to this really stimulating workshop. So I'm going to tell you about the work that's going on in my group and as well as in Andrew's group. We work very closely on the operation and scale-up of donor-based quantum computers in silicon. This is work that is funded by the Australian Research Council and the United States Army Research Office and takes place at UNSW Australia in Sydney, beautiful city. So the original idea for this kind of line of research came, in fact, from the University of New South Wales in 1998, where Bruce Kane was based when he wrote this seminal paper, where he proposed to use single donors in silicon to build quantum computers. So this is a cartoon that was published alongside the paper in 1998 and already contains all the ingredients that you need to build a quantum computer. So I'm basically going to go through them one by one through my talk and show you how we have built all these parts and how we operate them. So the first thing will be to talk about the physical qubits, so the spin of a single phosphorus donor in silicon, how we operate it, basically the single qubit gates, which are done by magnetic resonance, how to address the individual qubits. Of course, phosphorus atoms are atoms, so they're all identical. So how are you going to select in an ensemble of many phosphorus atoms the one you want to operate? And the Kane proposal already had an idea for how to do that. And then how you couple them together to make 2-qubit logic gates. Okay? So note that in the original Kane proposal, the distance between the qubits is very tight. It's about 15 nanometers. And I really hope that some of you have read the paper, and if you haven't, please go back and do it. Because the visionary aspect of the Kane paper really was that he was very upfront about the fact that in 1998, nobody could build this thing. Okay? He said, look, you know, this I think is a good idea, but no one knows how to make it. But there is $1 trillion semiconductor industry whose timeline and whose business model it is to follow what we know as Moore's law, which means that the size of transistors shrinks exponentially. So 15 years from now, in fact, commercial nanoelectronic silicon devices will have to be on the scale that I propose this device to be. And guess what? That's exactly where we are. We are now on the 14 nanometer node if you buy a brand new computer with an Intel chip. So this was really the visionary aspect of that. Now, let's start with the physical qubit, so the single phosphorus donor in silicon. This is the top right-hand side of the periodic table. Silicon is there. Phosphorus is just to the right-hand side of that, so it's got an extra positive charge that binds an extra electron at low temperatures with a Coulomb potential. And so the electron has a spin of a half, and the nucleus of phosphorus has 100% spin a half. So there's only one stable isotope. So these are, in fact, 2 qubits in one atom. Okay? And so you can really think of this as hydrogen in vacuum. There's a, spin a half positive charge and a spin a half negative charge around it. Now, of course, silicon isn't vacuum. It's a crystal with a crystal structure, a band structure. And silicon is special in that the minimum of the conduction band is not at k equals 0. It's at 85% of the Brillouin zone. So in fact, when you bind an electron in silicon, the ground wave function needs to be, well, any wave function needs to be built out of linear combinations of these 6 conduction band minima called valleys in x, y, and z. So in fact, the wave function, the 1s ground orbital wave function of an electron bound to a phosphorus donor in silicon doesn't look like the 1s wave function of a hydrogen atom. It's different in size, but it also has these funky oscillations at basically the atomic scale. So this is very pretty to look at, but it's not very pretty to work with, as I'll explain later on. All right, now how do you place a single phosphorus atom in a silicon chip? Well, there's various ways to do it. There is one method that is by STM lithography. That's what our colleague Michelle Simmons is working on at UNSW. But Andrew and I and our colleague in Melbourne, at the University of Melbourne, David Jamison's group, are adopting a very standard industry method, which is the ion implantation. That's how all the transistors in your normal electronic devices are doped. By essentially putting the chip inside of an ion implanter, you make a mask with electron beam lithography, and then you implant donors in there. So David Jamison's group has developed this method to actually count individual donors going in. We don't normally use the counted donors just because it reduces the yield, but the system is there if we needed it. I also want to point out that there is some really interesting development in the area of precision ion implantation that comes from the ion trap quantum computing community, oddly enough. So there's a group in Mainz that is an ion trap quantum computing group, but they're now developing this system where they cool down their calcium ions the way they normally do in their ion trap, and then they sympathetically cool another ion that can be nitrogen. They're working with people who do MV centers as well, but it also can be phosphorus. So they cool it down, and then they open the trap and they accelerate the ions out. They focus them with electrostatic lenses, and this can get 5 nanometer precision in when the donor goes. So this is a very, very exciting perspective. And the beauty is that the counting is done in the trap. You don't need to make a single ion detector on the chip. In the ion trap, you can tell when you have one ion, so it's very convenient. All right, so now let's say we've put our donor in there. We decided that that's what we're going to do. How do we operate that? So if you look at the spin Hamiltonian of a phosphorus donor in a magnetic field, when the magnetic field is larger than the hyperfine coupling, so this is the Hamiltonian, the levels look like this. So in a high enough field, the eigenstates are just the tensor products of electron and nucleus up and down. And if you want to manipulate these quantum states, you do magnetic resonance, and you'll find there are 2 frequencies to flip the electron dependent on the state of the nucleus, and then there are 2 frequencies to flip the nucleus dependent on the state of the electron. So in a field of, let's say, a Tesla, Tesla and a half, the electron frequencies will be, let's say, 40 gigahertz, the nuclear frequencies will be a few tens of megahertz. So what we do to deliver these microwave excitation to the spin is actually to fabricate on the chip a microwave transmission line. We've put a fair bit of microwave engineering optimization into making this line as effective as possible. And it's completely broadband. This is not a resonator. It's terminated by a short circuit at the tip, so it's fully reflective, but it maximizes the magnetic field, and ideally it brings the electric field to 0. So what you want is to have no electric field produced by this antenna so that it doesn't upset the charge detector in the vicinity. And this is completely broadband, so we just use a power combiner, and we combine the tens of megahertz excitation for the nucleus with the tens of gigahertz excitation for the electron. They do go down the same line. So it's a very compact, convenient system. So as I always tell my students, doing spin resonance on one spin is not any harder than doing it on a million spins like people have done for the last 60 years. The hard part is read out the single spin. That's the hard bit. So the way we do it is inspired by what was done earlier on in the gallium arsenide quantum dots community, and is to use what's called energy selective spin-dependent tunneling. So if you place your donor in the vicinity of a charged reservoir that has to be very cold so that the Fermi distribution of electrons in the reservoir is sharp on this energy scale, and you can line up the energy levels of your spin such that the spin-up electron state faces empty states in the reservoir, whereas the spin-down is facing occupied states, so that only if the electron spin is pointing up, it can leave the donor can be ionized, whereas if it's pointing down, it cannot escape. So this works if basically the electron Zeeman splitting is much, much larger than 4 or 5 times kT. So that's why you need Tesla magnetic field and a dilution fridge. For the nuclear qubit, what you do is you do a pi pulse on the electron on one of the 2 possible transitions that depend on the state of the nucleus. So for example, if the nuclear spin is down and you do a pi pulse, at this point you flip the electron up and then you read it and the electron escapes. Whereas if the electron is up, sorry, the nucleus is up, if you do that transition, that doesn't excite anything, so the electron does not escape. Notice that this is a QND readout. You can actually cycle and repeat this thing, so the nucleus is not lost. To detect the ionization of the electron, which depends on the spin state, we use a silicon MOS single electron transistor. This is the kind of device that Andrew discussed yesterday, and his group has been working on shrinking these devices to the point where they hold a single electron. You can use them as qubits. Here we use them as charge sensors, so here the dot may have maybe 100 electrons or so. Notice that this really is just a modified silicon MOSFET. If I didn't have these 2 extra gates, this would be a second-year electronic textbook MOSFET. There's only 2 extra gates here to isolate the quantum dot in the middle and tune the tunnel barriers. The way you actually use it is that you tune this single electron transistor in Coulomb blockade, so there is 0 current, when the donor is neutral. And then if the donor gets ionized, which is a spin-dependent process, as I explained before, the positive charge left behind by the ionization shifts the bias point of the single electron transistor, and if you tune it right, it goes on top of the Coulomb peak. So you get 100% contrast from 0 current to maximum current by removing 1 electron. So the data will look like this. For example, here is where you load an electron, then you go to the readout phase, and if you see that there is 0 current in the readout phase, it means that the electron spin was down and never escaped. If you see a trace like this, where there is this blip of current, it means that the electron spin up, escaped the donor, and then the donor was empty, and the spin down state is facing full states in the reservoir, so an electron spin down replaces it and shuts the current. So you get this single blip of current. And you also get, for free, the electrical reinitialization, the reset of your qubit, which is important, because the T1 is many seconds at this field, so if you had to wait for relaxation, you would be sitting there for a long time, whereas this goes in microseconds. Note, I'll just say this because I'll come back to that later. This is a projective electron spin readout, single shot. It's based upon the idea that you wait at this readout position for longer than the typical time that the electron needs to escape, okay? And this is what it looks like on the oscilloscope screen as you actually run the experiment. I always like to show this thing because it's very humanly accessible. Depending on what kind of science you've done in your life, sometimes you run experiments for a week and then you analyze data and you find out that you discover something. Here it doesn't work that way. You actually see it before your eyes, So these are just the single electron transistor current traces, and you see that there are periods when there's no current at all. And then at some point it switches and there will be lots of blips. So what we've done here is that we sit on one of the 2, nuclear transitions, so electron spin transitions dependent on the nucleus, and then every couple of seconds we switch the nucleus to the other state. So sometimes, we give all these pulses to the electron, and for a few seconds nothing happens because the nucleus is on the other state. Then we switch the nucleus, and every single time you get a blip. So every blip is an electron spin up being detected, you see with your own eyes in real time. And then whether there is a lot of blips or 0 blips tells you in what nuclear state you're in. Now, even before doing the whole analysis of the errors here, you can guess that the confidence with which you can tell me which state the nucleus is pretty damn high. I mean, you can't miss it, right? Just looking at it. So we easily get 99.9% fidelity on the nuclear readout, and we're at about 95% on the electron caused by basically the signal-to-noise ratio and the fact that sometimes some of the blips are too short for our bandwidth, so we miss them. But anyway. All right, so we've done some experiments, some of which were mentioned already by Andrew and also by John this morning, on natural silicon chips. Those were the first demonstrations of single spin qubits in silicon. I'm just going to jump straight into the latest experiments that we've done on isotopically pure silicon samples. In fact, we got these epi layers from our friend Koito in Japan. It's a 1 micron thick isotopically enriched silicon-28 epi layer with 800 ppm residual silicon-29, and silicon-29 is the only isotope of silicon that has a nuclear spin that therefore can cause this magnetic noise that dephases the qubits. So this is the actual SEM image of the device. So here you see the tip of the microwave antenna, there is the single electron transistor, and the donor is implanted somewhere there. So with these kind of samples, we get Rabi oscillations like this. These go on for basically half a millisecond if you have the patience to measure them. This is, really ion trap quality data, right? The line width of this electron spin resonance transition is something over 1 kilohertz at 41 gigahertz. So for anyone who has done magnetic resonance in their life, they'll understand that hitting a 1 kilohertz line at 40 gigahertz is really easy. It's great. It's really easy, really fun. So if you measure the coherence of this electron spin, we got about a millisecond Han-echo T2 time. If you do some dynamical decoupling, you get about half a second, which is already 10% of T1. T1 is about 5 seconds at this field. Okay? So you're coming close to the T1 limit already. If you do it on the nuclear spin, you have two options. You can use the nuclear spin when the electron is on the donor. You can remove the electron and just manipulate the nuclear spin alone and bring back the electron just to read it out. The coherence gets a bit better that way. And so this constitutes, as far as I know, the longest single qubit coherence in the solid state ever measured. It's 35.6 seconds. This is in a silicon MOS nanoelectronic device, okay? I want you to ponder on that. It's half a minute coherence in an essentially modified silicon MOSFET, okay? Okay, we've done some randomized benchmarking to look at the gate fidelities we get on the electron and on the nucleus. We got basically 3 nines on the electron and 4 nines on the nucleus. We've been working actually with the group of Robin Blum-Kohut, who is going to speak after me, on improving on this benchmarking of the fidelities as well as extracting what exactly our errors are. So this is a very interesting collaboration we have with Robin. He will tell you all about the method that he has developed for this. So these numbers are encouraging because they are above some of the most lenient error correction threshold that people know about. Now, going back to the electron spin measurement, remember that I was telling you, okay, you get a projective readout if you wait at the readout position for much longer than the tunnel time. What if you don't? Well, if you don't, then you have a weak measurement. So let's say I waited for only, this time interval here, which on this scale would be some, 20 microseconds. If I get zero current, it doesn't really mean that I'm sure the spin is down. But the longer I see no current, the more confident I become that I'm observing a spin-down electron. So in fact, once you think about it, this is the way quantum steering can work. So if let's say you start with a completely unknown mixed state, half spin up, half spin down, completely incoherent mixture. You don't know what's going on. You go to the readout position and you start watching your current. As time goes by and you still see that there is no blip, your confidence that the nuclear spin is down increases at this rate. So in fact, this is something we have used recently to improve what was really the last problem we were facing, which was that of initialization. You see, to initialize our spin, what we do is that we basically stay at the readout position. So if you have a spin up, it escapes, it's replaced by a spin down. If it's a spin down, it stays there. But so when you load the spin down, it comes from here, but you see, the density of electrons up there is actually not really zero. The temperature is not exactly zero. So we do have some initialization error that's of order 10% just because of the electron temperature. And that's, you can try and thermalize your system better, do filtering and whatnot, but there comes a point where it's too hard. So what we've done is actually quantum steering. So if you post-select on the traces where there has been no blip in the current for, several times the electron tunnel time, you get, better than 99%. This is a 99.2% trace initialization fidelity by steering. So here we just post-select the traces. We're now working on a real-time triggering where it basically waits for that, event to have happened before the actual manipulation sequence takes place. So the background here is basically because of the fact that there are some blips that are too fast and we don't detect them. With a little bit of improvement in the tuning of the device, and notice that also this data is measured, so the fact that we know so well what the state is because we have mapped the electron spin state onto the nuclear state and then read out the nucleus. So even though the electron readout fidelity is only 95%, the fidelity with which we can do electron-nuclear operations is better than 99.9. So you can map the electron on the nucleus, then read the nucleus, which has 99.9% readout fidelity. So you read it from there. So with a bit of optimization, Stephanie Simmons, who was in my group when this data was taken, has gotten this data, which is either the most exciting or the most boring data set you've ever seen, depending on your point of view. So this is a data set where she prepared 1,000 times the electron up, nucleus down state, and measured it. And 1,000 times you get, electron up, nucleus down. Just bam, 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 bam. You just can't miss it. So if you do the full, not just from this, but the full analysis of this thing, you find what she called the triple-triple. So there's 99.9 fidelity on everything: initialization, control, and readout through the nuclear spin. This is rare in the solid state. It's very rare. I think ion traps are there, but not many other systems, okay? And remember, this is in a silicon transistor, basically. Okay? All right, one other thing we've done, which is kind of a record-setting thing, I believe this is the highest violation of Bell's inequality in the solid state, so is to violate Bell's inequality by creating an entangled electron-nuclear state of the electron and the nucleus. I don't have the time to go into the details of how this was done. It's actually fairly simple. Really, the whole idea is to minimize every possible, initialization, manipulation, and readout error. As soon as you have some of those, your Bell number drops very quickly below 2. So the fact that you get 2.70 versus the theoretical maximum 2.82 is really like a one-number benchmark of how good the whole process is in your system. The thing I want to mention, because we have a talented artist in resident here, Milica, is that this thing got onto the front cover of Nature Nanotechnology through a collaboration with an artist at the College of Fine Art of our university, with whom I've been working for a number of years, actually. He has a whole project on creating an immersive art installation that has the aim of making you feel you are inside a qubit that is being manipulated. So I actually gave him raw data from my experiment, and he made this beautiful immersive art installation with sonification of the data and the rest of it. This is just a still image taken from there. It actually comes from real data when you think about it. So when I wanted to send a cover suggestion to Nature Nano for an entangled state, I said, well, how do you draw an entangled state? You can't do it, so you may as well express it as our artist friend does. So if you're curious about, successful collaboration between art and science, come and see me. There's a lot of nice stories to tell about this piece of work. All right, how do you address individual qubits once you have 1 million of them and they're all identical? Again, this was already in the Kane paper. The idea is to electrically control the hyperfine coupling. So your spin Hamiltonian is this one, and it contains this AS.I, which is the electron-nuclear hyperfine coupling term, which is basically proportional to the modulus square of the electron wave function at the nuclear site. So imagine you now have an electrostatic gate above your donor, and you can apply a positive voltage. You can suck up the electron wave function and therefore change the value of the electron overlap at the nucleus. So if you do it this way, what you can do is to coherently operate a locally selected qubit by having a continuous wave microwave that's always on, and by default your spin is off resonance with that, so nothing happens to it. If you want to operate on that spin, you then apply this local electrical pulse that Stark shifts the hyperfine so that then your spin becomes in resonance with the continuous wave microwave, and you can do whatever operation you want. Here is an example of a Rabi oscillation. It's just as good as the one you do by pulse magnetic resonance. We've done all sorts of other things. So this works. This is actually the A gate that's in the 1998 Kane proposal. Coupling. So in the Kane proposal, he suggested to use the exchange interaction between donors that, for that reason, need to be very close by. The exchange interaction is very short range, right? So this would be the Hamiltonian for two uncoupled donors. When you put them close together, there is this extra term that basically is proportional to the overlap of the electron wave functions. Now here is where the silicon band structure comes and bites back at you. So remember that beautiful fluffy wave function that I showed to you before. Now imagine you want to calculate the overlap of two of those things. Good luck. So this thing not only has the normal exponential decay as a function of distance of exchange interaction, but on top of that, it's got oscillations at the atomic scale. So it's pretty much impossible to really imagine you can put two donors. You really need atomic, but really atomic precision if you want to cast that in stone. One lattice site away, you can have an order of magnitude difference or more, okay? So my attitude has always been that rather than trying to make this exchange interaction some precise value, I want to have a scheme that is robust against it, that doesn't care exactly what value that is. And it turns out it's easy to think of it once you remember that 1 kilohertz line width that I was showing to you before. This is the electron spin resonance spectrum of a pair of exchange coupled donors as a function of the exchange that is here normalized by the hyperfine. So 1 is when J equal A. A is about 120 megahertz here. So the interesting thing is low J, where J is less than 100 megahertz. Then you got, there's basically, well, 8 lines here, these are the general. You get these ones here, the 4, 1, 2, 3, 4, the ones on the side, they are the electron spin resonance lines when the nuclear spins are in opposite state. So there's be these 4 lines here, and each one of them is a CNOT gate. Each one of these lines is flip electron, 1 when electron 2 is in some state. And you see that they're all separated by J, and then the 2 doublets are separated by about A, right? Now, with what fidelity can you do a pi pulse on one of these lines? Well, it depends on how close they are and how broad the lines are. Well, the lines are a kilohertz wide. And the distance, the A, is 100 megahertz. You got 5 orders of magnitude to play with, okay? So you can do some simple calculations and find out, if, depending how hard you drive the pulse and so on, what is the optimum fidelity you can get. If you have the 1 kilohertz line of isotopically enriched silicon-28, you can get 99.9% fidelity somewhere in some optimum. But even without that, you can get still 99% fidelity over at least 2 orders of magnitude slack on the exchange interaction. So this is the kind of thing that, at least in the short term, makes me confident that we can get it to work. 2 orders of magnitude we can manage. So we've actually started making devices where instead of implanting single ions, we implant P2 molecules. You can mass select them in the ion implanter, and then when the P2 molecule hits the silicon, it breaks apart, and the 2 atoms land at some distance that you can't really control, but more or less you can because it depends on the energy. And so we're still scanning for devices that have the atoms in the right place, but I'm confident we're going to get a 2-qubit gate working this way. How, long-term scalable that is, I don't know, probably not very much. So what if you want to do something a bit more future-proof than that? Well, so what you need to do is to forget about exchange interaction and look. Actually, it's already in the 1998 Kane paper, but for 20 years, nobody actually sat there and thought about it. It's already there in this little picture. There is an electric dipole here. Once you pull away the electron from the positive charge, you've created an electric dipole. It's always been there, we just never thought of it. So once you thought of it, then you realize you can do something which I think is very clever and very promising. Okay, so first of all, these are again the 4 states of the phosphorus donor. I normally would say, okay, if I make an electron qubit, I fix the nuclear state and let's say spin down, and these are my 2-qubit state, or I fix the electron down and these are my 2 nuclear qubit state. What if I take this pair of states as my qubit states? I call it the flip-flop qubit. So these are, electron downs, nucleus up, and the other way around. These states you can't address by magnetic resonance. The delta M is equal to 0, right? But you can address them by electric resonance. So the idea is that if you truncate to the subspace spun by these 2 flip-flop states, what you find is that, so the basis states are the up, down, down, up. Basically, the electron Zeeman minus the nuclear Zeeman is the sigma Z term in there. And the hyperfine appears like a transverse term. So if you just look at this, block sphere, you recognize straight away that if I can modulate the hyperfine at the frequency corresponding to the splitting of these states, then I can induce transition between these flip-flop states. So let's go back to the thing I've shown to you before already. So I'm sucking up the electron wave function with a gate. As I do so, my hyperfine interaction drops. If I pull it all the way out, this goes to 0. If I pull it halfway, you see that it's very sensitive here on electric field. This slope is very steep. So a small change in the electric field of this gate at the appropriate frequency will give me a big change in the hyperfine interaction, which therefore can drive transition between the flip-flop states. Plus, as mentioned before, I've created an electric dipole. So let's see how it works. The proper quantum mechanical way to treat this is to treat the charge state as a charge qubit. So you can set a charge qubit kind of basis, which is electron at the donor, electron at the interface. Those are the two basic states. And then there is a tunnel coupling in the charge qubit Hamiltonian, and then a detuning. And so then you write the hyperfine interaction as a function of the operator, the sigma, of the Pauli matrix that describes the charge qubit. And then you introduce an electric drive, so time-dependent Hamiltonian, EAC, cosine of some. You write it all together, and what you find is that if you dispersively drive, so in fact, you want to have the charge qubit energy splitting a little bit bigger than the flip-flop qubit splitting, so that in fact you never excite the charge qubit. It's a virtual transition. The charge qubit stays in the ground state, so you don't mix your clean, beautiful spin qubit with the dirty charge qubit. It's just a virtual process. You still get some 5 megahertz, driving frequency with incredibly small values of this electric field. We're looking at 30 volts per meter, right? It's very, very sensitive. Now, the beautiful thing is that you can do this even with the nucleus. So if in addition to the electrical drive that drives this electronuclear flip-flop state, you also add a magnetic drive that drives between the electron states, then you have effectively like a Raman process. So now you manipulate the nuclear states using two transitions that go, in fact, not exactly through the state. Again, you're a bit detuned from that to avoid the excitation of this higher flip-flop state. You can do nuclear manipulation at, half a megahertz rate with a tiny, gigahertz magnetic resonance field and a very, very tiny AC electrical excitation. Now, the coupling. We now have an electric dipole. If you now write the full Hamiltonian of two systems like this that have been pulled halfway to the interface, so they have this electric dipole, you write the electric dipole interaction as a function of the operators of the individual charge qubits and solve the whole Hamiltonian. I'm not going to give you all the solution here. It's in this paper. It's on the archive. You need to choose the tuning properly. But anyway, you can find easily a 5 megahertz coupling between the flip-flop qubits at 180 nanometer distance. This is a substantial coupling at a distance that is much more comfortable to work with than the 15 nanometers in the Kane proposal. Right? And then again, you can do it even with the nucleus. And amazingly, for reasons that have to do with what is the optimal way to tune the states when you do it with the nucleus, if you do this Raman transition, so you'll have this AC magnetic field in addition to the electric dipole coupling, you can couple two nuclear spins with a half a megahertz strength at, in this case, the optimal distance is 385 nanometers. I find this mind-blowing. Two nuclear spins, almost half a micron away, coupled by half a megahertz. Okay? Now, of course, if you have ever seen a cavity or thought about it, the first thing that you think is that, well, you have an electric dipole, you can couple to a CPW resonator like the transband people do. And indeed, you can do that. You can put in the numbers, and for the flip-flop qubit with a reasonably shaped cavity with a bit of a constriction to amplify the vacuum electric field, you can easily get a couple of megahertz coupling between the flip-flop qubit and the cavity. And even for the nucleus, if you add this Raman field, you can get a quarter of a megahertz coupling between a single nucleus and a microwave photon. I mean, I've been giving this talk for many months now, and I still find myself mesmerized at the idea that you can have a quarter of a megahertz coupling between a single nucleus and a photon through this process. Now, the other thing that most of you will think is, okay, you showed me this beautiful, super coherent spin qubit. It's got half a minute coherence and so on. And now you start mixing it with a charge qubit at a silicon oxide interface. I mean, that is all going to absolute hell, right? Maybe not, because as we already heard this morning from John, the power of clock transitions, these special points in the spectrum of a qubit where they are to some order, in the case of bismuth first order, insensitive to some field. In this case, we actually have a second order clock transition that makes it insensitive to electric field. Again, this comes from the full solution of the Hamiltonian. If you want to have an intuitive intuition of why that is, think of it this way. So the dashed line here is the energy splitting of the flip-flop qubit as a function of electric field. So you see it kind of starts high and drops. It's got a pretty steep slope here. And the reason is actually mostly because the G factor of the electron is different between the donor and the interface. So as you pull it up, the actual G factor changes, so the Zeeman term changes. But in fact, this flip-flop qubit is dispersively coupled to the charge qubit. The charge qubit has a dispersion relation that's a parabola that's got a minimum here at this tipping point between the donor and the interface. The scale here is compressed. Of course, this dispersion of the charge qubit is very, very steep. And when you have dispersive coupling between two systems, there is a dispersive shift. So in fact, the dispersive coupling between the flip-flop qubit and the charge qubit bends this energy of the flip-flop qubit. And if you tune it right, you can find a point where both the first and the second derivative of the flip-flop qubit splitting are 0 with respect to electric fields. That's second-order clock transition. We put in some numbers, and we find, expected coherence times that are basically comparable to those of the bare phosphorus left there by itself. Of course, we'll have to do it in the lab, but the maths is what comes out. Now, another criticism is that, so I've showed to you before that the exchange interaction is a real pain to work with because it's exponential and it's got these oscillations at the atomic scale. Now, the cynics, including a referee of the paper, which is it's a perfectly valid point, will say, well, all you've done here is to relocate your trouble to another place. Because now the tunnel coupling between the electron at the donor and the electron at the interface is also exponential in the depth of the donor in this case, and it's got these oscillations at the atomic scale. So have you really gained anything in terms of manufacturability and reliability? And the answer is yes, because I have no idea how to make a J gate like in the Kane proposal. So how to make a gate that is, we can make 10 nanometer wide gates, but to align them between two donors in the middle, I don't know, I'm not going to promise you that. Whereas here, I know how to tune this. So this is actually an atomistic time binding simulation of the tunnel coupling between donor and interface for a certain depth. And what you see is that if instead of just one gate on top of the donor, you make exactly the same gate stack that Andrew was showing to you yesterday to make the MOS quantum dots, so 3 gates overlapping with each other, you can actually displace the potential well at the interface sideways. You just bias the gates so that that potential well moves sideways. And doing that, you can tune the tunnel coupling by 2 orders of magnitude. This is something we know how to do. This is an MOS quantum dot. That's exactly the stuff that Andrew was showing to you yesterday. We know how to do that. It's a very different story than how to do a J gate aligned between two donors 15 nanometers apart. So I just want to mention here before concluding that this basically, when you put it all together, starts to resemble a lot certain ideas that people like Simon Benjamin have been working on of having kind of cells of, locally coupled qubits connected by long distance links. And he found that the fault tolerance thresholds are actually incredibly lenient. You can have even 10% errors on the links and up to some fraction of a percent on the plaquette on the inside. So the way you would implement, this is for a sort of ion traps, ideas, but the way you would implement that in our system would be like this. You can imagine having a 2-dimensional array of these donors with their gates on the top, and this coupled by electric dipole interaction on a scale of, let's say, 200 nanometers, which is pretty comfortable to work with. And then one side of that plaquette could be coupled to a microwave resonator that then couples it to another plaquette. Okay? So that's how you would implement this sort of architecture this way. So I want to stress here that the beauty of this is really the spacing. So 200 nanometers is a nice scale to work at. It gives a bit of room it gives a bit of tolerance in the fabrication. Also, I forgot to mention it, the electric dipole interaction, of course, goes like 1/r cubed. So if you have, 10 nanometer precision in the implantation, but your, target distance is 200 nanometer, whether it's 200 or 210, it really doesn't matter very much, right? So it's very robust in that sense. And then here you would have these microwave resonators, and you also have a lot of real estate in there. This drawing is not to scale at all. You can imagine in the middle of this having classical electronics that does some functions for you. This is all in silicon. So I would like to leave you with this picture and leave you to ponder to the potential of an architecture like this, made with a silicon MOS structure with essentially the best qubits we have in the solid state. So an idle qubit could be just the nuclear spin with the electron ripped off. Then you bring half of an electron wave function to it to operate, and then the 2-qubit gates are mediated by the electric dipole. We started making devices to actually demonstrate in the lab these things. So this is the first, let's say, microwave cavity device we've made. This is the actual cavity. We're doing some efforts to kind of shrink the gap at some point to maximize the vacuum electric field. This is the electric dipole device. It's basically two devices, two spin qubit devices face to face with a kind of slightly modified gate layout. You can see here is the magnetic drive line that gives the Raman field for the nucleus. And here are two coplanar waveguides that terminate in an open circuit to do the 40 gigahertz electric drive. These are all nicely impedance matched. And so this is done with a kind of 3-layer overlapping gates technology that is also used in the silicon MOS DOS that Andrew was discussing yesterday. So we're very excited about this progress, and we hope to have some experimental data to show you next time we meet. So with this, I leave you. I want to show the beautiful pictures of Sydney. Again, we have jobs coming there. I also want to show the beautiful people in my group. We are a very kind of cosmopolitan, international, sophisticated bunch of people. We don't have like group photos with, hiking boots and stuff in the mountains. We go to, nice cocktail bars with leather couches. Sometimes it gets a bit more rough, but, it doesn't matter. These are new people in my group. So if you want to be one of us, drop me an email. And meanwhile, thank you for your attention.
Okay, questions? Yes.
Yeah, something that I was thinking about when looking at your graphics, in terms of the this important second-order clock transition in the protection against charge noise for this this dipole qubit, right? This is a one-dimensional calculation, right? I mean, you're looking at the electric field in one dimension, and you're kind of assuming that your quantum dot is a blob that's sort of centered over the phosphorus, right?
Well, this calculation doesn't even make, all that goes in there is the tunnel coupling. So the way you calculate the tunnel coupling is with NeMo, with the full, atomistic type binding.
Well,
once you have the tunnel coupling, that just goes into a Hamiltonian that plugs in there.
Okay, but I'm looking at a plot where the axis is E sub Z.
Sure.
And there's going to be an E sub X and an E sub Y because you don't actually have a large planar or a perfectly symmetric gate. And I'm wondering whether those three-dimensional aspects of the electric field, which will, in general, pull the quantum dot kind of away in other dimensions from the phosphorus, can lead to a dipole term that
the honest answer is we haven't looked at that. I would be rather surprised if there is no second-order clock transition in that situation. We'll be at a different point. You'll have to tune it differently, but the general principle that the bare flip-flop qubit energy splitting has a slope, and that there is a dispersive coupling to the charge qubit, and that dispersive coupling gives you a bump, and if you align them right, the thing goes flat. I think that's pretty much independent of exactly which way it goes.
But will you be able to align them correctly with just one gate, is I guess what I'm getting at.
I see. So, well, with these 3 gates, basically. So your question is this gate stack sufficient to massage everything in the place you want? I don't know. I would like to hope that there's going to be some way to massage it in place, but we haven't looked in this detail yet.
Okay, we have a question here. If we can get a microphone.
If you're using dipole-based gates, probably it will be a bit difficult to do simultaneous gates between two different pairs of qubits because the dipoles will.
Yeah, that's right. So this is a very important point I didn't mention. Of course, the dipole interaction is not nearest neighbor. So this can be a problem or it can be a resource. I'm not, quantum graphs or quantum architecture experts by any stretch of imagination, but people who know these things better than me do tell me that high graph connectivity is good for you if you can use it. So the fact that even the second nearest neighbor here is coupled by 1/8 of the strength of the coupling to the first nearest neighbor is something that you might be able to use if you're clever about it. I'm not, but maybe someone else can take these things off my shoulder and think about what kind of connectivity would you want to use and apply if you had a two-dimensional array of these things coupled by electric dipole. Keep in mind, of course, that the coupling can be switched off very easily because the coupling is only on if the tunnel coupling of the charged qubits of this pair you want to make interact is exactly the same. So you don't have spurious couplings going by if you don't want them to be there. Right?
Time for maybe one more quick question. Yes, right up the back. Someone's going to have to run fast.
Oh, he comes ahead.
Hello. So I don't know if you already answered this question in the talk, so I apologize if you did. Okay. But how many qubit can you entangle at the same time, if you like?
Well, so far we have only successfully operated a single donor that contains 2 qubits, so there's a 2-qubit entanglement between the electron and the nucleus. We have seen, I haven't shown it in this talk, I have a bunch of slides, but there's no time to talk about it. We have measured the exchange interaction between a pair of donors. It was too strong to do any useful, quantum gate. We learned a lot about the valley physics of silicon. It was actually a whole interesting story by itself. But we have observed the exchange interaction. It was not of the value that was useful for us to make entangling gates. This is where we stand at the moment.
Thank you.
And we are working on making devices like this one, where we implant these P2 pairs with an energy such that the distance where they land should give us a fairly high yield of the exchange interaction being in the value that's useful for making entangling gates.
Sorry, do you, when you say you have job, you mean postdoc or PhD?
Both. I actually need more PhDs than postdocs, quite frankly. I'm having a hard time hiring PhDs. The young generation of students is suffering from huge FOMO, fear of missing out. They just want to try every lab in the world and have a little taste like bees, pollinating every flower. And it's really hard to make them commit to, come and work with me for 4 years.
Right, well, you can continue discussions about pollination. There's a cocktail bar we found around the corner with comfortable leather seats, which Andrea likes, so you can pollinate there later on. So at that point, I'll ask you to thank our speaker again.